So today I'm going to talk about improving structure prediction with locally normalized models. Essentially what I'll be telling you is that so locally normalized models were really popular at one point of time, and then they died. You had CRFs, and now they're back again with the resurgence of neural networks. So it actually it's important to look at why they died, and now that they're back, should we look at the lessons that we learned then to improve with locally normalized models. So first, I guess I'm going to use the pointer. So what are locally normalized models? So in this talk, I'm going to be talking about modeling conditional probability distributions. So somebody walks up to me with a sequence of words, x1 to xn. I mean, in this case, it's going to be a sequence of words, and the output is going to be either a structure or a sequence. So I'm going to be modeling conditional probabilities. Can everyone see the screen from there? Okay. So in a locally normalized model, the way it works is, so you first predict the output label, potentially conditioning on the entire input. You can grab features from the entire input, and you predict the output label. Then after you've predicted this label, you can condition on the previous label and potentially the entire input, predict the next label, and so on and so forth. So why is it locally normalized? Because the probability of an entire sequence, the conditional probability, is a product of these locally normalized probabilities. The probability of each yi is computed locally. Is this the red? How do I point with the? Oh, it doesn't point. Okay, so each of these probability distributions here is local across here, across this particular state. And what I mean by state is the amount of information you choose to keep from the input and the past. So for example, you might actually choose here. In this case, I'm allowing you to look at 2 positions before. You could look at 3 positions before, and then your state would be, three outputs in the past and your entire input. So the probability distribution is locally normalized across each state, and the probability of the entire sequence is a product of these probabilities. So versus globally normalized, where you have a notion, you have just like one state per sequence. So for example, you have pairwise factors, and the condition probability is computed by looking at the joint probability of the entire sequence at one time. And what happens in contrast, in a locally normalized model, the probability, it's only the past that affects the future, whereas in a globally normalized model, the past affects the future and the future affects the past. So you won't make a prediction of y1 until you kind of know what y sub n is. So what are the advantages of both of them? So MEMMs are really popular at one point of time, and I think this is better for me. Yeah, okay. So MEMMs are really popular at one point, and the advantage is that you have really fast training with locally normalized models. You just have to extract features from state and the action or label that you want to predict. In contrast, globally normalized models like CRFs are slow. In particular, if you have higher order features, higher order factors, then they're expensive to train because you have to do inference. Slow training kind of limits the amount of feature expressivity you have. In locally normalized models, you could potentially condition on the entire input and all the outputs that you've seen so far. But you have these non-global scores. You have the probability of a sequence is computed using these local scores, whereas globally normalized models actually look at the entire sequence. Now, why did this hurt us, right? So why is this a bad thing, and how does this hurt accuracy? So it's useful to think of, in this talk, the kind of models I'm going to talk about, it's useful to think of this particular abstraction. You have a state, and you predict an action which modifies the state, and you produce another action, and the probability of each action is locally normalized across the state, and the probability of the entire sequence is a product of these probabilities of the actions given state. So notice that this is a locally normalized sequence model. You can have locally normalized tree models. So if some of you know the work of Richard Socher, where you have these recursive neural networks, so that would be a tree locally normalized model. But I'm talking about sequence locally normalized models. So let's look at how wow, this scrolls really. It's really sensitive. So let's look at how label bias affects dependency parsing. So in dependency parsing, somebody walks up to you with a sentence, and you're supposed to produce this syntactic structure where you have heads and modifiers. It's a syntactic structure that only is built on words, and it models words and their modifiers. So here you have with, which is a noun modifying preposition. Sushi modifies eat, and you want to produce this dependency tree which is the highest probability dependency tree according to some model, some conditional model. So we're going to use the ARC standard system. This is going to be like a really quick refresher on what on the dependency parsing system we're going to use. So we have a buffer, we have actions, and we have a stack. And your state is a combination of these three items: stack, buffer, and one previous action. And you have shift. The actions available to you are shift, reduce left, and reduce right. So let's say you do a shift. You shift an item onto the stack. Here's another shift. Shift another item. And notice that you couldn't do any reduces here because you need at least 2 items on the stack to do a reduce. So then you can do a reduce right, or you could do something incorrect, which is a reduce left. Actually, a reduce right is incorrect here too, because as soon as you add a parent to sushi, sushi cannot get any more children, which it needed to have in the actual dependency parse. Whoa. Sorry. So if you added a parent to sushi, sushi can't have any more children in this ARC standard system. So that was the incorrect move to do. The correct move to do would be a shift, but that is something you could predict. And so the probability of the dependency tree is a product of the probabilities of these actions: shift, reduce left, so on and so forth, given state. I'm going to give this up. This is annoying. Sorry. This is it's going too fast. Okay, so the way you actually extract training data is. So you first, you run a canonical parsing algorithm. You extract, you have your state, and the label is the action. Then you in this case, this is the canonical parsing algorithm for the previous, for the example that I just showed you. So you do a shift, you extract some more state. Then you have another shift operation. Then you extract it. You extract the state and label pair. And now, once you have these state and label pairs, you train a classifier, your favorite classifier, to maximize the log probability of your pairs given, and to maximize the log probability of your pairs under the model, which is a conditional model. This is sort of standard. Okay, and then if you want to do decoding, you either do greedy decoding, or you do beam decoding. Now, what Zhang and Never observed in 2012 is when they trained. So standard training is you only look at the canonical goal path, and you train your local model. And when they trained a local model on just the goal path, and when they got a decent accuracy of unlabeled accuracy. So in this talk, I'm going to talk about unlabeled dependency parsing. They got an accuracy of 89.04. Now, when they took the same classifier and they added a beam, their accuracy dropped astonishingly, about 10 points. And they complained that this was due to label bias. So label bias. So let's see. How label bias, so this particular phenomena, label bias, that's peculiar to these locally normalized models, how it might occur in dependency parsing. So you're running your parser, you predicted the right action here, you predicted the right action here, and you could potentially predict an incorrect action here with some high probability. Your parser might not be, your classifier might not be perfect. So now you've actually ended up in a state that you've never seen in training. Now, because you've never seen it in training, you've never had data. You've never known what's the right action to take, and you could potentially take every action after that with very low entropy. And what that will result in is the incorrect tree would have higher probability than the correct tree, even though your actions from this point on are perfect. So what's happening here is these states, the actions from these states, don't compete with each other. So what the effect that you get is you end up choosing labels or actions that actually lead to states that have very low entropies. Here's something else that could have happened. You had the correct action prediction at this point, but because you've arrived in a state that you've never seen in training before, you could potentially have very low entropy from those states onwards. And even though you had decent accuracy for the right actions here, the total probability of the correct parse is lower than the probability of the incorrect parse. Simply because, so the label bias problem was that, it was originally noticed by Batu and solved by Lafferty, McCallum, and Fernando Pereira in the CRF paper, was that transitions leaving a state do not compete with transitions from another state. And what that results in is that you will choose actions that actually lead to states with lower entropy. So how could we potentially solve this problem? So we kind of need some competition between these two states. So we need some notion of what is a state, how good is a state, how good is it to be in a state? Okay, so let's imagine that somebody walked up to us and in addition and actually told us that this is a good state or this is the bad state. So this is our first assumption, that there's two kinds of states, good and bad, and you'll have probabilities assessing how good or how bad these states are. So somebody says, okay, this is a good state, we proceed. Okay, this is another good state, we proceed. Now your classifier makes an incorrect action, that's fine. You can't have perfect classification. And then somebody tells us this is a bad state. Since we know this is a bad state, we can choose not to proceed, and we essentially kill that parse, and the correct parse, even though its probability is low, actually ends up winning, and we get the right probability, and we get the right structure, even when you do a beam. So this is essentially the intuition. Now, how do we, so it would be useful if you could get notion of state quality, and there's only two kinds of states, good or bad. But now, how do we get this information, right? So, so first, what's been the related work in this area? So I like to call it recovery. Most of the related work has been recovery-based approaches, that if you end up in a bad state, what's the best thing that you could do to actually recover or get to a good parse? So CERN, which is sort of like reinforcement learning, what they do is that they have the optimal policy, which is take the perfect action, and they have and they interpolate between predictions from the model and the optimal policy, which kind of trains it to be robust to prediction errors. So CERN says that, well, at training time you're using gold data to train, but at testing time you actually use previous predictions. So to kind of bridge this gap, you should interpolate between these two policies. In dynamic oracles, which is more recent work, they do something similar, that if they're in a bad state, their oracle is no more the optimal parse tree, but they lower the oracle. They change the oracle tree to be the best possible tree that you can arrive at when you're in a bad state. So again, they're sort of training towards recovery. This is going to be avoidance. Well, and the strategy here is going to be, if you know you're going to beam at test time, you could potentially fall into label bias traps. So probably the right thing to do is actually avoid bad states. So again, we're going to need a notion of state quality. So the solution is joint probability. Earlier we basically had actions given states, and now I'm saying that you should model action and the class of a state, and the class of that state, given state. So in the case of dependency parsing, this could be a categorical distribution having 6 items, but we're going to choose a different factorization. So the rules of conditional probability say this has to sum to 1. And now the question is, what do we do when the state is good, and what do we do when the state is bad? So if the state is good, then you should take the right action. Now if the state is bad, so actually, I mean, I'd like to say that there's another way you could factorize this. You could say that probability of action comma class given state is probability of class given state times probability of action given class comma state. We're going to take a different sort of more intuitive approximation to this, or sort of a different factorization. So if the class is bad, then we make another assumption that you should have absolutely no preference over the next action. It should be a maximum entropy distribution, so it should be uniform. So if your class is bad, then the probability of an action, given that the class is bad, is uniformly distributed across the probability that this is a bad state. So what does that give you? Instead of actually modeling 6 items, the product of these two, you just model 4. You just model sort of a categorical distribution with 4 items, where you have probability of action given class is 1, which is kind of what we modeled before, and the probability that this class is actually 0. Now you notice that in some sense, all this is doing is it is stealing probability mass. So if this state is truly bad, it'll steal probability mass that's available to taking an action, and if it's completely bad, then you won't move further, because you only want to move further in your belief that this is actually a good state. Are there any questions? Yeah.
When you enter a bad state, because it's something you've never seen in your training data, can't you back off your probability estimate or something?
So the parser that we're going, this is sort of moving ahead. The parser that we're using is a sort of it's a priority queue parser. So if you end up in a bad state, even if let's say a parser is very likely, if you end up in a bad state, it becomes extremely unlikely, and what was next most probable comes up. So you have this, with the parser that we use, you kind of get backtracking behavior. We will end up getting backtracking behavior. I'll talk about it. I'll describe the parser later on. Was that your question?
Not exactly. Like, in the case of the eating sushi and tuna and so on, is the problem that you just haven't seen tuna in the data set?
Oh, no, it's that you haven't seen, it's that when you only train on a canonical gold path. So there's multiple problems. One, there's multiple ways of getting the correct parse. We don't even consider all possible ways of getting the correct parse. We only choose a canonical. There's derivational ambiguity when you're parsing. There's multiple ways of parsing the same sentence. We only choose one. Second problem is that your classifier could potentially make errors, and you're actually conditioning on previous actions. So you're in a state that you've never seen in training because you only trained on the goal path. And when you're in a state that you've never seen in training, you don't know what to do. It's possible that there are actually some features that are super likely for taking an action, but it's the wrong action at this particular state. So that's the problem. The problem is you're in a state that you've never seen at training time.
Couldn't you look for similar states and smooth them?
I think maybe the dynamic oracles might be doing something like that. They might be getting some smoothing behavior, but I'm not sure. But this is going to be some more of an avoidance. If you're in a bad state, identify it and don't move forward. And empirical results will actually show that this works quite well. So now what we needed to do was we want to model both the class of a state and the action. So now we need to actually manufacture training data. Earlier we only needed to model state and action. Now we need to model class, state, and action tuples. So how do we do that? So we run our standard sort of canonical parsing algorithm on the training data. It's sort of similar to before. And now if the state is correct, we actually label it as C equal to 1, and we extract that tuple. Here we get another state, we label it as C is equal to 1. Now, remember that you needed at least 2 items to do a reduction, to do a reduce on the stack. So this is the correct action to take. Now for every feasible correct action, we take every possible incorrect action and we manufacture a bad state. So we only move one step forward, primarily for computational reasons. But what we do is, for every correct state, we manufacture a bad state and we label it as 0. Notice that there's no action here. There's only a class label. And again, here's the right action, and for every correct state, we actually manufacture bad states, and we extract. And that's how we extract these sort of tuples for this particular scenario, where we're modeling class, action, and state. Was there any questions about how we model?
So you're essentially synthesizing negative.
Exactly. Right. So this is, in some sense, this data is available to you. We just never use it, right? So there's exponential number of bad states. So we only move one step forward. And a part of future work is how do we cleverly explore these bad states. But this data is available. We just never used it when we were parsing. So let's use it. And all we do is move one step forward. So in adherence with modern times, we use a feed-forward neural network to model probability of action, class given state. And how does it look? So it's a two-layer hidden neural network, and the hidden units are rectifiers. So they have this nonlinearity when you get the. Are people here aware of rectifier linears? Yeah. So they have a lot of advantages. They don't suffer from saturation issues. Your inputs are features. We used 2 classifiers. We did 14 or 25 features, and your output is this categorical distribution with 4 items. So to a point to note, all the neural networks in this I built with my own sort of computational graph framework. So there's LSTMs that come forward as well. And there were some contributions from David and Victoria, but I have these models that I build myself, so I can easily prototype. And I tried with a bunch of different architectures, and this seemed to have the best balance of speed and accuracy. And the way we train it is that we extract action, class, state triples, and we train the feed-forward neural network to model action, class, given state. We try both options. So we train using mini-batch gradient descent. One other thing, so I use dropouts, and I use dropout in these 3 different sites. It's more important to use dropout here and here, not as much there. And dropout seems to help quite a bit. So I try with both pre-trained embeddings and randomly initialized. And when we decode, we use beam search with 14 features following Huang and Sagai, and we use best first search with 25 features. It's like a priority queue parser. So how do we pre-train embeddings? So I took the blip corpus, I concatenated it with the Wall Street Journal. I trained a 7-gram language model with a 100,000-word vocabulary, and I use noise contrastive estimation. So this is kind of my other work. I've done a lot of work on training really fast neural language models with very large vocabularies. This is my own toolkit. You can download it. It works really efficiently. The architecture is very similar. So you have 2 hidden states. the softmax is essentially very large because it's a 100,000 word vocabulary, and the noise contrastive estimation, the noise contrastive estimator allows us to train these language models rapidly. So the input embedding dimension is 64, which I use in these experiments. The output is 512, which I'll use later on in my LSTM experiments. And again, we train with stochastic gradient descent to maximize, very similar to before, we maximize the probability of the triples under the conditional model, and we adjust the learning rate based on the development set. So now for accuracies. So these are the graph-based parsers in the literature. Martins et al. Is this it's turbo parser. Zhang and McDonald is a higher order Q pruning graph-based parser that uses Q pruning. Zhang and Nirez is a transition-based parser that uses this really expressive feature set. I think they use like an XS and a lot of feature templates. They have a lot more features than we use. We only use feature types. We don't do conjunctions because we rely on the neural network to do conjunctions for us. So Chen et al. was the first parser to do were the first to do neural network greedy parsing, and their baseline is 91.8. Weiss et al. Last year, their greedy parser gets 93.2. In contrast, our pre-trained baseline parser outperforms Weiss et al.'s parser, and when we add these error states. So the Weiss et al. Parsers, their parser is a bit. It's kind of a mix between globally normalized and locally normalized, because up to this point they do only locally normalized. But from here on, what they do is they pre-train the parser to be locally normalized. Then they fine-tune the softmax layer with a perceptron that actually does global parsing. So it's kind of a mix between locally normalized and globally normalized. This is these are pure locally normalized parsers. And when we add our error states, we call them error states, we get 93.7. And then when we do ensembling, we actually train a bunch of neural networks and we allow them to vote. We do a mixture, we get some more gains. So to sort of see how good is the model and the framework, we ran it without pre-trained embeddings as well. And even our baseline, even without even a randomly initialized neural network, outperforms a previous pre-trained parser. But most interestingly, when we add error states, we outperform a graph-based parser. And this is a really fast parser. I mean, currently it's at 950 words a second. And there's a lot of optimizations, but it works fairly efficiently, and it outperforms a graph-based parser that uses higher order features. On the Yamada-Matsumoto dependencies, again, we get really strong improvements, outperforming previous graph-based parsers. Our randomly initialized parser does really well too, and when we apply error states on pre-trained embeddings with ensembling, we get to 93.7 that outperforms previous graph-based parsers.
How big is the data set?
It's about 1 million. On the training data is about 1 million tokens, and the development set is about 40,000 tokens. So it takes about so essentially the data has now tripled in size, because for every correct action, you could potentially be extracting three incorrect states. So if there's if you're extracting n tuples before, now you're extracting 3 times n tuples in our case.
So training is 1 million stuff.
Yeah, training is 1 million. Training is 1 million tokens. Yeah.
And the testing?
Testing is about 80,000 again. That's section 23. These are results all on testing. So it's section 23 is about 80,000 tokens. To sort of see whether error states are kind of an indirect evidence of whether error states are helping us, I fired a counter if the probability that this was an error state actually was above 0.5, so it's majority. And it turns out as the sentences get longer, when you begin to start getting these search errors, that's when you get a lot of these error states, indicating that it's actually starting to help us when we have longer sentences and we have potential for search error. Now, I mentioned that, so I'm just going to check the time. So I mentioned that we are using a best first parser. So the way it works is you have this priority queue, and the most likely parse is on top, and we pop it, and then we expand from it. So it's possible that every single time we pop the most likely parse, it actually turns out to be a bad state. So the right way to measure how much work we're actually doing is the number of pushes, because each time we generate a new state, we push it onto the priority queue. So if you notice that it's more or less linear, but as sentences get longer, you actually do more pushes. In general, it's quite fast, but you could potentially be doing You could potentially be popping out and pushing, because when sentences get longer, you get a lot of error states. So you could potentially be popping and pushing again. Because it's a best first parser, there's no way to bound its complexity. But I believe the average beam size when I computed here was about 5 or 6 pushes per sentence. But yeah, I mean, I can't say this is O of n or O of n squared or n cubed, because you could have pathological cases where you just constantly push and it's bad. The most likely parse always turns out to be a bad state. Any questions? So essentially, so this is the dependency parsing part where we saw this label bias issue that was hurting us in accuracies, and the point was that the reason why label bias occurs is we have no notion. One reason why, if we had an idea of the quality of states themselves, then potentially we could kill bad states, and when we explicitly model them, we find that we get nice gains in accuracy. And in some sense, this is nice also because, as somebody pointed out here, this data is available to you, but we never use it. And on that, we only move one step forward. Potentially, we could follow our sort of generative story that this is once you're in a bad state, the distribution of our actions is uniform, and we could move farther, but for computational reasons we don't. That could potentially improve our accuracies even more. So now shifting gears, we're going to go into a more pure neural model. So I'm going to talk about pure neural models for CCG supertagging, and I'm going to describe how, if we look at label bias and CCG supertagging, we can improve CCG both supertagging and parsing accuracies as well. So in supertagging, essentially somebody walks up to you with a sentence, and you have to plop these little trees on top of these words. So you can think of supertagging as almost parsing. If you have a perfect supertag sequence, then the parsing algorithm that generates the CCG parse tree is almost deterministic. So now what's happened is that the ambiguity has kind of been pushed onto the tagging task rather than the parsing task. So so here this is so you have this noun modifying preposition that takes a noun to the right and returns takes a noun to the left and returns a noun. You have eat that takes a noun to the right, a noun to the left, and returns an S. And again, we're going to be looking at conditional probabilities. So the probability of a supertag sequence is modeled is modeled as a conditional probability. So there's two desiderata in supertagging. So you have long-range dependencies between words, where so here you'd have width that needs information to the left and needs information to the right. You can imagine that this is a much longer sentence. You'll have supertags that are really complicated, that need information from far back in the past. So just to give you an idea of the difficulty of this problem, there are about 1,200 supertags as compared to pause tagging, which is about 45. It's definitely easier than machine translation, because in machine translation you can imagine that there's millions of tags. So it sits in between. Most tags are infrequent in supertagging. And you also need consistency. What do I mean by consistency? So if this is expecting an n to the left width, then the supertag of the word on the left should be an n. So based on so what if people, so the training data, it's again section 02 to 21, it's 1 million tokens. For supertagging, the development section is section 0. I believe it's about 40,000 tokens. And the test section is the same as for dependency parsing, section 23. So what's been done in the past? So Lewis et al. Used a feed-forward neural network independent supertagger. It's greedy, so you go over each position and you predict the supertag independently, and they get about 91.5% supertagging accuracy. So last year, Xu et al. Had an RNN. Again, it's independent, and they use the same suite of features that Lewis et al. Use, which is they look at a word window of size 7 and they extract suffix features, so on and so forth, and they get 93.1. So I trained my feed-forward model, exactly the same architecture that I showed, without pre-trained embeddings. I use a more restrictive set of features. I use a word window of I use a word window of three around the centered word, and I use the suffix. I use suffix features I use the suffix of the center word itself. And when I train my model without pre-trained embeddings, I get 92.6. And when I train it with pre-trained embedding, it outperforms the previous baseline. And I also, sort of for completeness, I also tried an MEMM, which does suffer from label bias, and it gets 93.1. Interestingly, at training time, this got 95% accuracy on the development set. But when I actually deployed it at test time, because we're using previous predictions, it's an MEMM, and previous predictions could be wrong, the accuracy actually drops. But the point of this slide also is that there's a tendency to use these complicated models, but if you train your feed-forward models really, really well, you should max out the accuracy that you can with your feed-forward models to actually see what the true baseline is. And you can see that you can do really well with the properly trained feed-forward model.
What is significant differences?
Oh, in both these models?
Yeah.
Yeah, so I mean, probably not, but the differences lie actually in the computation time in particular. It's really fast to train this model. And also hints towards the architecture should be motivated by the model, right? So are we really gaining anything by the RNN versus, versus the feed-forward is capturing all the information, right? So, if you're capturing information by a less expressive hypothesis class, it says that that particular problem was not as hard as we originally thought it was.
So
right.
You're saying it's faster. Can you give us a time comparison?
Oh, so I don't know Sewardall's parser, but the feed-forward model that I use, it would be unfair to give a comparison because I'm able to train it within 2 hours on the million-word corpus. But I use like the Intel math kernel library. I use Eigen to do all the matrix heavy lifting, and I use like multiple cores. So if he didn't use that, but RNNs are generally. But the LSTM models that I'm going to present use the same optimization, but they're slower. So RNNs are generally slower because you have to do a lot of back propagation through time. Oh, another thing is I use a lesser feature set. They use 7 word windows. I just use 4 word windows. So the point here was that if you sit down and train your models, if you train simpler models well, you could potentially get good accuracies that were not evident before. We are going to improve these accuracies, and the point here is that baselines were not as strong as we originally thought they were. Okay, so the first desiderata was that you need long-range dependencies. A natural model is a bidirectional LSTM, and the way it works is so you have a forward. I'm not going to describe what people here are probably aware about a long short-term memory recurrent neural network. So each of these blocks is an LSTM block. So you have a backward LSTM that's eating these input words and creating these hidden vector annotations. And you have a forward LSTM that does the same. And you have a combiner. It's an ensemble that takes these 2 hidden vector annotations. It linearly transforms them and passes them through a rectifier nonlinearity. And then you send it off to a softmax output, which then computes your distribution across supertags. Oh, one point to notice in all the experiments that we do, typical thing in supertagging is you have cutoffs. We don't do any cutoffs. We just use all supertags. And we do have an UNC token to account for the fact that we might actually see unknown things. But if there's a supertag at test time, the test that we didn't see at training, we of course get it wrong. We definitely get low frequency supertags, some of them wrong. Some of these analyses are actually, detailed analyses are in the paper, but we don't use any supertag sort of frequency cutoffs that people normally did. And another thing is in the LSTM work that I'll be talking about, I don't use any features. I just use pre-trained word embeddings, so it's a much simpler model. Okay, so now here's some comparison and some ablations. So when we train a feed-forward model, we get 93.3. When we only train a forward LSTM, which potentially can only look at the subjects of verbs as it's moving forward, it gets really poor accuracy. A backward LSTM can look at the objects of verbs, and kind of these are the supertags that are the hard ones to get. So a backward LSTM for an SVO language like English is probably better. It would be interesting to try it on a different language to see how the forward and backward compare. And when you combine both directions with a bidirectional LSTM, we see that we get the benefits of both their accuracies, and we get an accuracy of 94.1, which outperforms state of the art. Any questions? Okay, so we sort of check the first point. We have long-range dependencies between words and supertags. So how do we get consistency between supertags? A natural way would be to actually. So when I say consistency, so what we did was we actually took our supertag sequences, and we ran a parser, a deterministic CKY parser. This is Jonathan Bisk's parser. We extracted CCG rules from the tree bank, and we ran them on our supertags to see how parsable are these sentences. And turns out that the feed-forward neural network has decent parsability. The forward LSTM and backward LSTM you can only parse about 40% of sentences, and you get and the backward LSTM, the bi LSTM parses about 81% of the sentences. And this indicates that, so parsability is a notion. I mean, if the supertags are inconsistent, you will not get parsability. So this indicates that the bi LSTM is sort of getting consistency across words. Now, how can we push this further? So a natural way is to actually add a language model on top of the supertags. So this is an LSTM language model. The way it works is, here's the previous supertag. The language model generates its own hidden vector annotation, so which is again fed to a very similar ensemble. It linearly transforms these both hidden vectors, and it passes it through a rectifier, which then goes to a softmax. The way it works is, you have the language model which generates a hidden vector annotation. You predict the supertag, then you feed in the supertag because it's a language model. You predict the next supertag, feed it in, just like a standard LSTM language model. And when we train it, it turns out that the accuracy actually drops a bit than from the pure bi LSTM. But that should not surprise you based on what I've been saying already, that what's been happening is that you've been training on these goal supertags, but at testing time, you conditioned on previously predicted supertags. So notice that the language model actually uses the previously predicted supertag. So at testing time, you're conditioning on previously predicted supertags, which are potentially incorrect, and then that causes drops in your accuracy. And to sort of kind of zoom in and see how this drop is happening, so I computed the perplexity of the actual supertag sequence under both the goal supertag sequence and the predicted supertag sequence. So certainly this is the perplexity of the predicted supertag sequence will be low. But what's the gap? So this is the correct sequence. Ideally, this should be extremely low, but it's not. There's a decent perplexity gap between these two. So at testing time, the goal sequence is not likely under the model. So what can we do to lower this? What can we do to lower this, bring this curve down?
So in your previous slide, like you're saying that the performance drops, it's 0.2%.
Yeah, yeah.
So how significant is that? Because so essentially training neural networks is highly unconvex. So have you tried like restarting it and see if it's always the case, or for this specific initialization?
So you can think of restarting. So I ran a huge grid search with different dropout probabilities. So it's somewhat like restarting, but I have not tried taking my optimal dropout configuration and then restarting about 100 times. They take long to train, so I had only had patience for running all the dropout configurations, but it's possible that it might recover, but this is not going to improve. This is going to happen. This will stay. This problem will stay. So what we do is we do something that's actually that's been done by we use scheduled sampling, which has come from Google, and more recently I discovered that there's another strategy that we were trying that Ranzaro et al. more recently tried as well, and this paper is at ICLR, but the Bengio paper was from last year. So what happens in scheduled sampling is you flip a coin, and then you say, okay, if it's heads, then you're actually going to use the predicted supertag. So you can think of scheduled sampling like online CERN. So CERN first sort of went over the data and generated these predictions. This does it in an online fashion. It kind of generates. It uses predictions from the model versus the goal supertags in an online fashion as the training is moving along. So you flip this coin, and then if it says heads, then you actually use the predicted supertag. If it says tails, then you use the argmax. Use the most likely predicted tag from the previous position. So what we do is we also use the previous top five supertags, and then we renormalize them and we feed them again as input, so sort of to get previous distributions, and that also kind of encodes some ambiguity, and you kind of get some path-like behavior that you're transmitting. So we try both the argmax and the previous five top supertags, and if it says heads, then you'll use the goal supertag again. And the probability of heads or the probability of tails increases as your epochs go along. So as your training goes along, you want to use predicted supertags more than you want to use gold supertags, because you finally want to bridge this gap between training and testing, right? So that's what we do. So and we use an inverse sigmoid schedule. As over time, you end up using predicted supertags more. So now you get this desired effect. You actually see that. So I haven't drawn the bottom curves. Still, all models do, the predicted sequence is still the most likely one, but there's some clutter here. I can show you, what I'll tell you is that you still get this behavior, but what's happening is that the gold sequence has become more likely now under these predicted, when you train with scheduled sampling. So we do get gains in accuracy. The gains in accuracy are not very large, but one advantage is that you kind of still get consistency as well. So in addition to getting small gains in accuracy, we improve consistency. Now you notice that when we did this gold training, we get 96.5% parsability, which is quite high. When we do the scheduled sampling, we actually lose parsability. Well, I mean, when you think about it, it's not too hard. I mean, you can see why. So what's happening is here, if you make a mistake, you're being trained to recover from that mistake. So what happened here is that as it was testing, it made a mistake, but it's been trained to recover from that mistake. Now making a recovery is actually being inconsistent with something that you previously did. So you lose some parsability. But when we do this transmitting of 5 previous supertags, we get nice parsability as well. So supertagging is all good. What are the effects on CCG parsing? Xu et al., when they trained there and had the previous state-of-the-art parsing at 87.0. Now, we were using the most recent CNC parser. I forget the version number, but it's a Java parser, and you can download it. We use a standard off-the-shelf parser. We used a cutoff of 10e-5, so we only kept supertags that had probability greater than 10e-6. And we didn't have a part-of-speech tagger, so we also ran our part-of-speech tagger on the supertags. And another point is, so it's there in the paper, feed-forward neural networks are excellent. They can also be excellent part-of-speech taggers, which shouldn't be surprising. But what's surprising is that if you train an MEMM neural network part-of-speech tagger, they're so good that you barely get any loss. So I guess label bias will probably happen when your classifiers, your local classifiers, are not very strong in the first place. A neural network MEMM part-of-speech tagger is excellent. So because the original baseline, we used different part-of-speech tags and a different parser, we retrained the baseline, we retrained a parser with the baseline super tags, and their accuracy improves to 87.5. Now, when we train with the CNC parser and our part-of-speech tag, so these are all with the new part-of-speech tags. Oh, I forgot to mention sort of one important thing. So with the BiLSTM, for the BiLSTM, we use greedy decoding. We only pick the most likely super tag. For the BiLSTM LM, we do beam search, similar to what people did in neural machine translation. And for the scheduled sampling, because we're kind of taking the previous super tags, we just use greedy again. And the advantage is that it's much faster, it's more, you get better consistency, and it's more accurate than the other parser. Well, it's as accurate as scheduled sampling 1, but the advantage by using scheduled sampling or transmitting the previous 5 is that you actually just can do greedy decoding. Yeah. So when we retrain the CNC parser for CCG parsing, we end up getting 88.4% CCG parsing accuracy, which is currently state of the art. And to give you an idea of how, when you do parsing, you can potentially get parse failures. So with scheduled sampling 5, we are not able to parse 2 out of 2407 sentences on the test set. The baseline didn't parse 1, but our retraining, when we retrain the baseline, this parses all sentences. I forget how many we miss here. But we penalize ourselves for not parsing any of the sentences. We don't get any scores. We don't get any additional points for parsing these sentences. We don't get any partial credit for the dependencies that you can extract from unparsed sentences. So to summarize, locally normalized models are kind of back because simply, and they're kind of back because earlier what happened was we were using these maximum entropy models. So your local classifiers are maximum entropy models. Now we have these powerful mechanisms to model very expressive states. Like for example, LSTMs could potentially crunch a lot of information in the past and create new state. Neural networks can take a whole number of features and produce state representations, but they can suffer from search errors. And modeling state quality is a simple and effective solution. And what we did in the previous approach in dependency parsing is in sort of kind of stark contrast with what happened before. There was no notion of modeling how good the state was. And when you're having these locally normalized models, and in particular when you're doing beam search, you can definitely fall into these traps where these states are bad, and you have no control over outgoing distributions, which could have low entropy. So modeling state quality is a very useful notion. Modeling state quality I believe is important to actually evaluate where you're at. And you can and in the last part, I showed how pure neural models can also benefit from mitigating label bias. So, so there's been some kind of similar work in dialogue management with these error states, but the framework, the probabilistic framework that I presented today this is the first time we've kind of someone's actually come up with a nice story for, if you want to model state, what would be a nice probabilistic approach to this, and what are the assumptions that you're making. And later on, I mean, if people are interested, there's some interesting. So you can think that every in the dependency parsing work, you can think that every action sequence that goes through a bad state under our probabilistic model, its probability is lowered because earlier, if you didn't check it, if you didn't control it, if you were in a bad state, you could potentially have probability 1 for an incorrect action. But now, if you've correctly identified a state as bad, it has probability, every action is probability at most uniform. So what's happening is every action sequence that goes through a bad state now has its probability lowered. So in some sense, if the correct action sequence went through only good states, and every incorrect action sequence has now its probability lowered. So now you're kind of getting this nice margin. So there are some extensions. There are some sort of more theoretical investigations that I want to do with this, because we're kind of getting this. We're creating these margins between bad action sequences that pass through bad states and good action sequences. So the work that I mentioned. For every, to the second point, so one thing that I didn't talk about is what do you do when the action space is large? So let's take machine translation, right? For every correct word, there's like potentially 1 million incorrect words. So it's not feasible to generate bad states, but there are solutions. You could only look at the top 5 most incorrect states, because you have to compute the softmax anyways. So you have an idea of the distribution, so you could make the problem tractable by only looking at a subset of the bad states. So you can think of some relationship to reinforcement learning here, where you can think of a bad state as a state that has negative infinity expected reward from the future. I've been trying to see if there's a much deeper connection, but I haven't been able to discover. I mean, I think there's some interesting connections there. If some of you are aware of the contrastive estimation work by Smith and Eisner that actually sort of looked at these local neighborhoods and tried to move probability mass from bad local neighborhoods into the correct sequence, this has a sort of similar feel. This is not the end. There's other approaches, for example, to sort of alleviate label bias. For example, you could imagine running models in 2 different directions and kind of doing some kind of dual decomposition, trying to do dual decomposition, where you try to make forward and backward models actually agree on their predictions, and that could alleviate label bias as well. But what I mean is, this is kind of the beginning. I think we should start looking into this to potentially sort of improve our accuracies on the tasks that we're using these locally normalized models. Yeah, so some other stuff that I've done, or the other strand of work that I've done is on neural language models. So I mentioned that I used the noise contrastive estimation approach. So we were the first to do integrated machine translation decoding. So we actually added neural language models inside the decoder. The difficulty there is that computing the softmax is super expensive. And if you don't, because you can't normalize over 1 million items. So what we did was we trained models with noise contrastive estimation that were self-normalized. That is, a normalization constant was very close to 1, so we didn't have to compute it. We could talk about it later if people are interested. So more recently, we have a paper on training large vocabulary LSTM language models on the GPU. We get very good perplexities. So we had this sort of a fun project that came out of this was with Leila Wehby and Tom Mitchell at CMU, that we found that if you use representations from RNNs and feed-forward models, they're quite decent at actually predicting MEG signals inside the brain. So kind of guess what word people are thinking of. And more recently, I've been trying to investigate a more sort of a more theoretical connection between noise contrastive estimation and maximum likelihood estimation. So maximum likelihood estimation is a standard way to train language models, and noise contrastive estimation is a much cheaper alternative. So instead of renormalizing over 1 million words, you can just use 100 noise samples. But if you use a mathematically motivated initialization, which we do, it actually makes training very stable. So what ends up happening is that the gradient that's coming from NCE and the gradient that's coming from MLE are very similar in the beginning. And we've been sort of been trying to establish this relationship, and we're doing more work in this. But if people are interested, it's quite interesting. I'd be happy to talk about it. So this talk was there were two kind of papers that came out of this talk, or this talk is made out of two papers. One is at TACL 2016, and one is going to appear at NACL 2016. Thanks. Any questions?